Okay, I'm going to talk about AI, um, partly because you can't avoid doing it anyway. I I've done a lot of programming over my life, and I've thought a lot about these things. So this is going to be related to, in a strange way, to some of the things that Pankaj was saying earlier, but also in other areas. So I hope you find it interesting. I told Dave that this was going to be Dave Colella, also a MITRE person, and Gary Jason is sitting next to him, that this was going to be a math talk about non-mathematics with a non-mathematical conclusion, which therefore made it about mathematics because it's a double negative. So here we go. All right, so recently, open mind, I mean, deep mind, excuse me, that was a slip. DeepMind is a company that was started in Britain and acquired by Google. And they've been very interested in developing advanced AI models, not always LLMs, but frequently. But their models have always been based on a particular idea, and that is of gamification. So we'll talk about that a little bit. And they recently announced, last year, I believe, that they were able to perform at the, quote, silver medal level on the International Mathematical Olympiad. And they solved one problem within minutes. Good for you guys. And took up to 3 days to solve the others. I think some of the contestants would have legitimately cried foul, but that doesn't mean it wasn't an achievement. So it's one of a series of models that DeepMind has developed. Alpha Zero was really a chess model, and AlphaGo was a Go model, probably the more famous one. And they all followed these two models were particularly developed with this gamification strategy. That is, you teach the model the rules of chess, for example. You know, you can capture en passant and things like that. And then the model would play itself and play itself for millions and millions and millions of games and draw conclusions about the structure of chess. It wouldn't look at the historical corpus of chess games, which is quite large and a really good data set because they've been doing algebraic and PGN notation for years and everything gets recorded. But then they tested it with that and they thought it did pretty well, and then it managed to achieve certainly grandmaster and even beat world champions. So it was a major accomplishment. One of the things that, and then AlphaGo was similar. Go is a more complicated game in chess. It's a 19 by 19 square rather than the 8 by 8, so there's more possibilities. And maybe the rules are a little bit different, but they did so well that Lee Sedol, if I'm pronouncing that correctly, from Korea, was then one of the best Go players in the world, resigned from tournament competition because he felt that AI was unfair competition. And that was sort of a shame, but it was more than sort of a shame, it was a tragedy. And at least DeepMind had the grace to retire from competitive play. I mean, it is sort of like entering your Porsche Cayenne in the 100-meter dash at the Olympics. I mean, it would be strange, to say the least. But what gets really interesting is that the Alpha Star, which was a model based on a video game, which was trained in the same way, and beat regular players handily until it was pointed out that, well, it's directly wired to the controls. It can respond much more quickly than a human could ever respond. And so they put in lags, and then Alpha started losing. Rather spectacularly in one case. So they don't talk about that part too much. Then there's alpha tensor, which was an attempt to make, and a successful attempt to find algorithms for doing matrix and tensor multiplication. That was fine. The alpha proof is the one I want to talk about, and this sort of at the end of that lineage. So, oops. Well, what's going on here? I think if I push something, it will, or maybe, I'm sorry, what? Oh, it's a mouse. Windows. Where's the go button? Screen sharing, share. No?
Yeah, I think we might need that, right?
Okay.
Let me.
Never debug under pressure.
Is the
Double click?
no
What is this, Google Slides?
what does control?
Escape.
Right. L. All right, that was not it. Because that's actually that's the browser, not the Adobe.
Oh,
This guy? No.
present. There's there.
Present.
There we go. Okay.
Can even hide the. And the more there is something that's hiding.
Hide video
control.
panel.
No, the one below, the hide floating. That one.
That guy. Okay, there we go. Sorry, now catch up. But now this isn't working. Okay, well, I just. What's going on here? No, I know it's not advancing.
Yeah, big one.
On the board?
No, the mouse. This one was pretty big. This one now it's right there.
Okay, there we go. Blah, 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 blah. Okay. So this is a summary of what it was doing with AlphaGo and Alpha Chess. And one of the things this is what started really disturbing me when I got into this, was that there's sort of a breathless type of publicity going on. Ultimately, it rediscovered human patterns, accumulating thousands of years of human knowledge in a matter of days. I think that's a little overblown, but okay. And it ultimately discarded some in preference of new discoveries. Okay, so how are these discoveries achieved? They're achieved by tree search. They're not achieved by any sort of train of reasoning or something. So is that a discovery, or is it simply picking up a pretty shell on the beach? There are far more chess games in the span of all possible chess games than there are in the set of all games that humans have ever played. I've seen estimates of 10 to the power in the tens of thousands of possible chess games using the FIDE rules. And certainly the lowest estimate I've seen was 10 to the 120th power by von Shannon. And that's vastly more than humans have ever played since the beginning of time. So it seems natural that it would find things that humans haven't stumbled on. All right, so their master plan for alpha proof, and this is what I think is crucial, is they were using lean, which is, I'll talk more about lean in a little bit. I think it's wonderful. And it's an environment to explore mathematics rigorously in situ, in silico. But it's the second thing, is that we can reach superhuman intelligence and discover new truths, just like in Go, chess, tensor decomposition, provided we can get high enough quality plus quantity problems and reinforcement learning works, which is like saying it'll work if it works. So alpha proof is an agent that is sort of a mixture of artificial intelligence techniques. It uses an LLM strategy on known solutions to contest problems. So they took a large corpus of problems, not just from the IMOs, but also Putnam exams, et cetera, et cetera, et cetera, always limited to this sort of coset of exams, a cohort of exams that are basically high school level mathematics problems. And moreover, in one of the crucial features of these problems, that they're all problems that have solutions. They know a priori that there's a solution. Okay, so guide a specialized search tree, blah, blah, blah. Evaluates the results using lean. Great, I'm all in favor of that. And here's some, I've stolen a lot of things from OpenAI's documentation so that I can't be accused of just liberally interpreting things. So I want to talk about the formalization process. So what they're saying is that given, once they've encoded all of these problems, and they've run them through an LLM to produce sort of candidate proofs, then they have to have a way to translate these proofs into lean, the formal typesetter. Lean doesn't prove things for you. It's a calculator. A very, very sophisticated calculator and extremely difficult to learn, but it's a calculator. So it will evaluate, if you give it a sequence of implication statements, it will determine whether or not it is a tautology, which makes it a theorem. And so that's sort of a different thing. It's not doing any reasoning as such. Now it's a big deal, because I don't know about you guys, but I have trouble with the reasoning part sometimes. But one of the problems here is to translate what one would call informal mathematics, which is everything that all of us do, into a fodder for lean. Because lean can't read informal mathematics. And so this is a so-called formalization problem. And this is a big problem in proof design, computer-aided proving systems. And it's one that I'm actually getting very interested in, and we have someone attending who's working on this from Korea. Kathy, is she here? There she is. She's been working on formalization in her graduate work in Korea. So this formalization thing is difficult. It's not easy. It takes a lot of mathematicians working to formalize it. Okay, just to say a little bit about lean, it's a programming language, really. It's in the class of programming languages, it's a functional language, which puts it in the category of languages like Lisp, Mathematica, Rust, Go, a bunch of others. Julia to some extent, small segments of Python. Anyway, it's a functionally based language, but based on dependent type theory, which is a branch of logic which is now being argued as a potential replacement for Zermelo-Frankel. Okay, so proofs in lean are decomposed into what they call tactics, which are sort of, I think of them as a logical subroutine. You know, it's like, it's pre-coded lean ideas, which you can then use to assemble more complicated things. But to do even the simplest thing in lean is you wind up rewriting half of Principia Mathematica just to get there. Anyway, that's that. So proofs in leans are decomposed in tactics, and which, as I say, simplify the at time tedious translation of standard and formal mathematics into the formal representation. And so there is a large community effort, open source effort, to develop a library of lean tactics and proofs to translate much of the existing structure of known mathematics into lean. So then if you need a theorem and you're formalizing it, then you can call it as if you would call, I don't know, now my mind is blanking. Orthonormalization routine, Gram-Schmidt. If you know, it's a subroutine. Hahn-Banach theorem is a subroutine. All right, so there exists a large and growing library. They've translated a lot of stuff, but not nearly enough. And so that's kind of interesting. But then writing proofs becomes a sort of programming. Okay. And so I don't know that I object to that analogy all that much, but go on. All right, so alpha proof training, they have these informal problems. They parse them with an LLM to break them into pieces. And then they train the LLM to break those pieces into lean type tactics. Then they evaluate the tactics. Then people look at the tactics and say, is this going to work or not? And then eventually they use that to feed their tree search, where they come down with candidate proofs for different types of problems. Okay. So it's a process, and it takes a lot of work. So they fine tune with about 300,000 stake tactic pairs, and they're extracted from human written proofs. And this process takes not only, it's not just automated, it takes the intervention of a lot of human mathematicians. So that's sort of hidden. However, in fairness, when they run the test, then it's all automated. So they've got the model pre-trained, and this is typical in artificial intelligences. When you work with a large language model, all of those weights have already been trained. It doesn't learn from what you say to it, which I think is partly security and partly practicality. Okay, so blah, 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 this is what they're saying it, but so this targeted learning adapts to the fruit, doesn't matter. So my problem with all of this is that when you look at this and you look at AlphaGo, is you're working with a closed system. Okay, so you take, for example, in the case of chess, you take the rules of chess, you check the setup of the board, and then you go. That's everything is contained in it. Leibniz had that idea in his universal computing ideas, that you could generate all of human knowledge from a set of rules and assumptions and logic and so forth. A bit of a problem there. Alpha proof is not that, it's what I would call a half-open system. It's half open because it requires human intervention to make that auto-formalization. And I think that little auto-formalization process is the gateway into an opportunity both for mathematics and perhaps for artificial intelligence in general. So I would like to assert that mathematics is fundamentally open. I think Pankaj made that argument exquisitely well this morning, which I really appreciated. It's not just because first of all, we bring in physics, but we bring in all sorts of stuff. I mean, I can't imagine an LLM trained on mathematics up to, say, 1800 to come up with non-Euclidean spaces. And earlier yet, it would not have invented complex numbers. And so we expand the field of mathematics by research. That's really the purpose of our research. Our research isn't so much about proving theorems, although that's the metrics we use, but our research is about expanding and finding new and useful forms of mathematics and better ways to understand the world. And we take it from physics, we take it from medicine, we take it from everywhere. Sociology, for Christ's sake. So it's fundamentally open. And so the real question is not whether alpha proof can solve MMO problems. It can. It does that beautifully, sort of. They only solved 3 of 6, by the way, and it took them several days, but they'll get better. Oh, and also I should say, one of the problems, they had to use another system called alpha geometry. So it's sort of like the $64,000 question helpline, rescue line. So the question is not whether it can solve IMO problems, but whether it can, if it's operating within a fixed formal language, do what mathematicians have been doing for centuries. And I think that is the the real problem. And this all goes back to this philosopher, C. West Churchman, who was actually a professor of business administration at UC Berkeley and one of the early operations research gurus. He trained with Singer at Harvard. And he wrote a book in 1971, which almost no one has read, but he goes through and characterizes different types of inquiring systems. His goal was to understand how scientific inquiry could be aided by approaching computation. And this is what we're all doing here. So I think that's interesting. All right, so a bit more about formalization, because this I think is really important to the mathematics community. And so it's a process of translating mathematical arguments into a language that can be checked in Lean. This is the official logo of Lean. It really appeals to undergraduate math majors. But it's far from solved. Alex Kantorovich, Rutgers, has done a lot of work on this. And also Clarence Tao and Ken Buzzard at University College London. And it's been shown to be really interesting. Buzzard, for example, is trying to formalize the proof of Fermat's last theorem. So this is a huge project, and no one's expecting it to be wrong, but you never know. But it would be nice because that would get this whole corpus of mathematics into MATLAB, into MATLib, excuse me, not MATLAB, that's something else. Moreover, Terence Tao has done a lot of work on this. He's been translating all of the solutions in his advanced calculus text into Lean. And he's worked a lot with using Lean for collaboration. And the idea about using Lean in collaboration is you don't have to trust your co-authors quite so much. And the idea then is, and that's not to cast any shade on Chris and the frog, but you know, there's a certain extra burden in writing papers. I wrote one with John and George Binky a few years back, and I'm sure they had a great deal of trouble checking my work. I certainly did checking theirs. But that's it. So formalization, it could be a really useful way to do collaboration. The only trouble is it takes almost longer to translate the argument into Lean than it takes to come up with the argument to begin with. And so this is the proverbial long pole in the tent that's holding things up, because no one wants to do that. Ain't nobody got time for that. Okay, it's just hard. And so what is really needed, and what Kathy and I were talking about earlier, yesterday, was this idea of some sort of intermediate translation step that you could have some sort of automatic assistance in translating informal mathematics into Lean. That would be lovely. However, there's another long pole in the tent that I wanted to mention before I shut up. Let's see, I'll get to the conclusions. So yesterday at the dinner, it became even more obvious to me than it would normally have been, is how important community is in mathematics. Mathematics is not, and maybe all science is this way, but mathematics is a social, I'm not going to say social disease, it's a social blessing. And I think that we need to foster that. And I think the idea that we can gamify mathematics and turn mathematics into, all of mathematics into something resembling a TI-84 is absurd and pernicious at best. So that's my message. And so let me just get to my conclusions. Yeah, I'm almost out of time, almost. So my conclusions are, first of all, hats off to DeepMind. Alpha Proof was a monumental task. It took an immense amount of work, and it had moderate success. So great. Bravo to Alpha Proof. Does Alpha Proof presage the end of mathematics? No. So the results were obtained by pattern matching search algorithms and so forth. And let's suppose it were. So Socrates talks about the oracle problem. Suppose you had an oracle that could answer truthfully any question you put to it. Would it do you any good? No, because the answers to the question are not the point. The point is the journey to the answer, and that's where the real stuff happens. And so proofs, theorems, even published papers, wonderful and necessary as they are not the body of mathematics. The body of mathematics is a living thing. And you pass it down in a familiar way. Now go get the Mathematical Genealogy Project tells us that. Okay. On the other hand, I think formalization is a worthwhile goal. I think it could save us a lot of time. It could revolutionize training students to do proofs. And I'm even going to start doing it in my junior college classes. Might as well, they're not going to learn anything else, so they might as well learn something useful. No, that was cruel. But there's this development of MathLib, excuse me, I think is a really good thing. There are other proof assistants, but what makes Lean different is MathLib, and that's what I propose that one should do. Also, I had mentioned earlier Terence Tao's involvement both with the Lean community and also, I think, crucially with expanding cultural awareness of mathematics, which I think we really need. And hats off to him for that. And then finally, Kevin Buzzard's program to verify the proof of Fermat's last theorem. So if anybody is interested in joining that effort, I can give you a URL. But I think that he's a brilliant mathematician and a very snappy dresser. But I strongly recommend looking at all of that. And so that's what I have to say. I've got a bunch of references here if anybody's interested in following this. When I started doing this, when I was invited to give the talk, I thought, well, gee, this is Chris and Dave, and they did this cool thing of a guidebook to wavelet theory. I don't think that's what you called it, but it might as well be. Wavelets for dummies, maybe. But the idiot's guide to wavelets. But it was a monumental work, and I thought, geez, maybe I could do a little bit about talking about an approach to AI, in which that time I was thinking about things like transformers and large language models and so forth, and maybe giving sort of a mathematical guide and maybe pointing out some areas which might be of interest. But then I started learning about it and decided that doesn't seem very interesting to me. And but this other problem of which is not really a problem in mathematics, is sort of a problem in sociology and history and blah, blah, blah. And so I thought that was important. So now, as I said at the beginning, I'm concluding my math talk of a non-mathematical subject with a non-mathematical conclusion. And the conclusion is we need to do more of the things that make mathematics unique and valuable. And if we can find ways to make the things that are not unique and valuable easy, we should do it. So thank you very much.